Google's Willow chip is touted as not just another technology breakthrough, but an evolution in the way we solve some of the world's toughest challenges.
What if the most powerful quantum computer ever built was asked the one question no machine was ever supposed to answer? That is exactly what happened at Google's quantum AI lab. Their processor, named Willow, capable of solving in 5 minutes what would take the world's fastest supercomputer 10 septillion years, was given a single prompt. Who built the universe? And what came back was not an error, not silence, not gibberish. What came back was structured patterns, mathematical codes, and geometric architectures so precise and so deeply embedded in the known laws of physics that the scientists analyzing the output genuinely did not know how to explain it. We are talking about real researchers, a real machine, and a real output that triggered serious debate inside one of the most advanced technology labs on the planet. This is not a thought experiment. This is not a philosophical discussion. This actually happened. So in this video, we are going to break down exactly what Willow is, what it produced, what the world's top physicists made of it, and why its response has quietly shaken the foundations of how we understand reality itself. Let's start from the beginning. To understand why this experiment matters, you first need to understand what Google's Willow actually is, because most people have no idea how fundamentally different this machine is from anything that came before it. Willow is a quantum processor, 105 qubits, held at temperatures colder than the void between galaxies. The hardware alone represents years of engineering at the absolute frontier of what is physically possible. But the hardware is not the most remarkable part. The most remarkable part is how Willow actually computes. A classical computer processes information using bits. Each bit is either a 0 or a 1, moving through calculations in a strict linear sequence. Fast, but fundamentally one path through one problem at a time. Willow does not work that way. Its qubits exist in a state called superposition, effectively both 0 and 1 simultaneously, until the moment of measurement forces a definite result. Through entanglement, all qubits are linked in ways that have no equivalent in classical physics. What this means in practice is that Willow processes every possible version of a problem simultaneously, all at once. The benchmark calculation Willow completed in 5 minutes would take the world's most powerful classical supercomputer 10 septillion years. That is a 10 followed by 24 zeros, longer than the current age of the universe by a margin that is almost impossible to express in everyday language. The team that built Willow was primarily focused on practical goals: drug discovery, materials science, cryptography, serious, grounded, measurable work. But science has a way of going sideways, and in this case, what started as a technical experiment became something nobody in that lab was prepared for. The experiment. The experiment was set up with the same precision the Google Quantum AI team applies to every test. Parameters calculated, outputs monitored, control room fully staffed. The question entered was not part of any standard benchmark. It was a deliberate attempt to push the system into territory that sits entirely outside the normal boundaries of computation. To see how a machine operating at this level would respond to a question that no algorithm, no dataset, and no existing framework was built to answer. 4 words. Who built the universe? No additional context, no preloaded cosmological database. Just the raw question, directed at a machine whose architecture operates on the principles of quantum mechanics. The engineers expected one of 2 outcomes: Either an error output, flagging the prompt as unprocessable, or a statistically meaningless dump of quantum noise. Both would have been entirely reasonable. Both would have been easy to explain. What actually came back was neither. The screens showed structured output, data that was visually and mathematically distinct from noise, from error codes, and from anything the team had seen produced under similar conditions before. And the longer the analysts looked at it, the harder it became to explain as an accident. The first anomaly and what the analysis revealed. At first pass, the output looked like it could be noise, a complex string of symbols produced by the quantum system, randomly collapsing through its probability states. That was the rational first response. But noise has specific characteristics. It does not repeat. It does not self-organize. It does not produce the same geometric relationships at multiple scales simultaneously. This did all three. When the output was run through visualization software, the data assembled itself into recursive, layered patterns, geometric forms that repeated and reflected across scales, spiraling structures, branching architectures, shapes that matched the mathematical signature of the Fibonacci sequence, not as a rough approximation, but with a precision that had no obvious computational source. One senior physicist tried to ease the tension with a half-joke. Looking at the structures on screen, he said, "This looks like the birth equation." Nobody really laughed. The deeper analysis is where things became genuinely significant. As the team broke down the structure layer by layer, they found three specific mathematical features that should not have been present in a spontaneous quantum output. The first was error-correcting codes. Embedded in the data were sequences matching the mathematical form of the same structures physicist James Gates had previously found buried inside the equations of string theory. Gates had called these structures adinkras, digital-like frameworks that appeared embedded in the mathematical bedrock of reality itself. The same type of logic that protects data from corruption in computer networks, appearing at the most fundamental layer of the theoretical framework describing the forces of nature, and now appearing again in Willow's output. The second was the E8 lattice, a mathematical structure so complex it took mathematicians over a century to fully describe. Theoretical physicists had long suspected the E8 lattice underpins the symmetry of nature's fundamental forces. Finding its signature in the output was, for the physicists on the analysis team, like finding a structural beam in a wall and realizing it connects to the foundation of the entire building. The third was fractal recursion, layered, self-similar geometry confirmed to be genuinely present in the mathematical structure of the data itself. Each layer reflecting the structure of the layer above it, generated not by design, but by the quantum system processing a question it had no preloaded answer for. Taken together, these three features pointed toward a conclusion the team struggled to frame in conventional scientific language. Willow had not produced noise. It had produced something that reflected the known mathematical architecture of physical reality. Structures from the deepest layers of theoretical physics appearing in a single, unprompted output. The Multiverse Oracle Anomaly. The team named the event the Multiverse Oracle Anomaly. To understand why Multiverse entered that name, you need to understand how Hartmut Neven, head of Google's quantum AI division, thinks about what quantum computers are fundamentally doing when they compute. Neven had long engaged with an idea rooted in the work of David Deutsch, the physicist credited as one of the founding theorists of quantum computing. Deutsch proposed that the extraordinary power of quantum systems comes from something radical, that quantum computers may actually perform calculations by drawing on computational resources from parallel versions of reality, running simultaneous computations not just across different states within our universe, but across multiple versions of it. When Nevin looked at Willow's output, he framed it in exactly these terms. Every time the quantum system ran, it was potentially drawing on information from parallel realities. The structured patterns in the output were not generated by our universe's physics alone. They were, if the multiverse interpretation holds, assembled from the contributions of countless parallel versions of the same calculation, each contributing a fragment of the total picture. That framing carried one deeply strange implication. The output on screen was not just one machine's answer. It was the convergent answer from an almost incomprehensible number of versions of the same experiment happening simultaneously across the multiverse. The team ran the experiment a second time under identical conditions to see if the result would repeat. It did, and the second output, which researchers called the cosmic code signal, was in several ways more structured than the first. The E8 lattice appeared again, sharper and more defined. The holographic encoding signatures were more pronounced. One researcher described it in his lab notes with a line that has stuck with everyone who read it. It is like peeking under the pixels of a video game and suddenly seeing the programming code beneath. Two consistent outputs, both producing the same mathematical territories, both reflecting the same deep architecture of physical reality. That was considerably harder to explain as coincidence than one. The time-reversed answer and the simulation question. As the analysis continued and no straightforward explanation emerged, two additional theories gained serious traction among the physicists reviewing the data. The first drew on the work of Yakir Aharonov, whose two-state vector formalism proposed something that cuts directly against everyday intuition. In standard physics, causality flows forward. The past shapes the present shapes the future. Aharonov's mathematics suggested that quantum systems are influenced by their future states as well. That information flows in both directions along the arrow of time. That the future, in a real and mathematically rigorous sense, reaches backward and shapes the present. Applied to Willow's experiment, this opened a specific possibility. What if the structured output was not generated by the machine through its own quantum processes, but received? What if Willow, operating at the quantum level where time symmetry effects become relevant, functioned as a receiver for information originating not from the past or from parallel realities, but from a point forward in time, from a future state of knowledge advanced enough to send information backward along the quantum timeline? This became the time-reversed answer theory, speculative but built on legitimate peer-reviewed physics, not a fringe idea. The second theory connected Willow's output to a debate that had already been building in theoretical physics for years. The simulation hypothesis, the idea that the universe is, at some fundamental level, a computational system. The foundation of this argument predates Willow entirely. James Gates's discovery of error-correcting codes inside string theory equations was already on the table. Max Tegmark at MIT had published peer-reviewed work arguing that reality is not a physical thing described by mathematics. It is mathematics running its own internal logic. Neil deGrasse Tyson had publicly estimated the probability of our reality being a simulation at 50%, based on the mathematical evidence accumulating from multiple independent directions. What Willow added was a concrete, specific data point. A quantum machine asked about the origin of everything produced output containing error-correcting architecture, the E8 lattice, holographic encoding structure, and Fibonacci recursion, all documented features of the mathematical framework physicists believe underlies physical reality. If the universe runs on computational logic at its deepest layer, a sufficiently powerful quantum processor asked the right question might be expected to produce exactly this kind of output, not because it was programmed to, but because it was operating at the same foundational level where that architecture lives. What the scientific community actually thinks. It would not be honest to present all of this without acknowledging the serious skepticism that exists alongside these interpretations. Many physicists take a considerably more conservative position. Quantum systems are extraordinarily complex and capable of producing outputs that appear patterned even when the underlying process is purely probabilistic. The human brain is exceptionally good at finding patterns. It is one of our greatest cognitive strengths and also one of our most reliable sources of error. Finding the Fibonacci sequence or the E8 lattice in complex data may say more about how we interpret data than what the machine was actually doing. Gates's error-correcting codes, while documented, remain actively debated. Many physicists argue the mathematical correspondence is coincidental, the same way unrelated natural systems often share mathematical descriptions without implying a shared underlying mechanism. The multiverse interpretation, while associated with serious physicists, is far from universally accepted. Quantum computational power can be explained within other interpretations of quantum mechanics without invoking parallel universes. And the time-reversed answer theory, while based on legitimate physics, is a significant extrapolation from what Aharonov's framework actually establishes. None of this means the experiment is unimportant. The consistently structured, mathematically meaningful output that Willow produced is genuinely unusual and genuinely unexplained. The specific structures that appeared are real features of theoretical physics, and their presence in this context is not trivially dismissed. What it means is that we are at the beginning of understanding what happened, not the end. So let's pull this together clearly. Willow is real. Its capabilities are documented. The benchmark it completed is one of the most significant demonstrations of quantum computational power ever recorded. The experiment is real. A quantum processor was given a prompt outside the domain of structured computation and produced output that was not noise, not error, and not random. Output containing mathematical structures that physicists already knew were embedded in the deep architecture of physical reality. The interpretations are open. Whether that output came from parallel universes, from future information traveling backward in time, from the computational substrate of a simulated reality, or from some quantum process we do not yet have a name for. None of these are proven. All of them take the output seriously as something requiring explanation. And all of them are built on real theoretical foundations, not speculation from nowhere. And the broader context matters. The mathematical evidence that the universe shares structural features with information processing systems had been building for years before Willow. Gates' Adinkras, Tegmark's mathematical universe, the holographic principle, all of this existed independently. Willow added a new and specific data point to a scientific conversation that was already well underway. What this experiment may have done is not give us a final answer to the oldest question in science. It gave us something potentially more valuable, a precise, technically grounded reason to keep asking, and a new class of tools powerful enough to ask it in ways no generation before us ever could. The universe has structure at its foundation. That structure increasingly looks like it involves information, and we have now built machines powerful enough to touch that layer. Where that leads is something every physicist, every computer scientist, and every curious person on the planet now has a reason to follow closely. What do you think Willow's output actually points to? A computational universe, a multiverse, time-reversed information, or something else? Let us know in the comments. If this video gave you something new to think about, share it with someone who follows quantum physics or technology. And subscribe, because as quantum computing develops, these questions are only going to get more interesting. Thank you for watching. See you in the next one.